Hello, my name is Kyle Rojek, and today I'll be solving a problem where we are given a 10 centimeter long capillary tube containing both equal amounts of volume of liquid H2O and liquid D2O, and are asked to solve for the total mass flux of the system at time equal to 0.01 seconds. In this problem, we are given the molar diffusive flux of H2O, the molecular weight of D2O, and the mass concentration of D2O. So to start out, I'm going to write the definition for the total mass flux, and that is equal to the total mass concentration multiplied by the mass average velocity. So solving for the total mass concentration first, we know that that is equal to mass concentration of H2O plus the mass concentration of D2O. And we know that the mass concentration in this terms of H2O is equal to the mass of H2O divided by the total volume. And this can also be written as the mass concentration of H2O multiplied by the volume of H2O divided by the total volume. And since we know that these two liquids are taking up the same amount of volume, we can see that the volume of H2O is equal to the volume of D2O, which is then equal to 1/2 the total volume. So plugging in that information to this equation, we get the mass concentration of H2O multiplied by the half the total volume over the total volume. And the total volumes are able to cancel each other out, leaving us with 1/2 the mass concentration of water, which is 1,000 kilograms per meters cubed. Multiplied by 1/2 is equal to 500 kilograms per meters cubed. And solving for the mass concentration of D2O in the same way, and using the given mass concentration of D2O in the problem, we get 1/2 times 1,110 kilograms per meters cubed, which is equal to 555 kilograms per meters cubed. So adding these two values together, we get the total mass concentration, which is equal to 1,055 kilograms per meters cubed. And next, we want to solve for the mass average velocity. And we know that the system is closed, making the sum of the molar diffusive fluxes equal to 0, making the molar diffusive flux of D2O equal to negative 2.78 moles per meter squared per second. So next, using the definition for the molar diffusive flux, which is equal to, in this case, the molar diffusive flux of water is equal to the molar concentration of water times the mass average velocity of water. And we know the molar concentration is equal to the number of moles of H2O divided by the total volume. And we also know that moles is equal to the mass of H2O over the molecular weights divided by the total volume. And we know that the mass of H2O is equal to mass concentration of H2O times the volume of H2O divided by the molecular weight over the total volume. So using the same process for when we were solving for the mass concentration, we know that the volume of H2O is equal to half the total volume. Being able to cancel out the total volumes leaves us with 1/2 mass concentration of water over the molecular weight of water. And since we know these two values, we can plug them into the definition for the molar diffusive flux of water. And since that is equal to 2.78 moles per meter squared per second, that is equal to 1/2 the mass concentration of H2O over the molecular weight of H2O multiplied. Okay, so 1/2 the mass concentration of H2O, which is 1,000 kilograms per meters cubed, divided by the molecular weight, which is 0.018 kilograms per mole, multiplied by the mass average velocity of H2O. And doing the same process for the molar diffusive flux of D2O to solve for the mass average velocity of D2O, we get negative 2.78 mole per meter squared per second is equal to 1/2 the mass concentration of D2O, which is 1,110 kilograms per meters cubed over the molecular weight of D2O, which is 0.020 kilograms per mole, multiplied by the unknown value of mass average velocity of D2O. So solving for each of these respective values leaves us with a mass average velocity of 1.0008 meters per second for water, and a mass average velocity of negative 1.0008 meters per second for D2O. And so we know that the total mass average velocity is equal to the sum of the mass fraction multiplied by the mass average velocity. That gives us the mass concentration of H2O times 1.0008 meters per second mass average velocity of H2O plus the mass concentration of D2O multiplied by the mass average velocity of D2O all over the total volume. And so solving for that, we get the mass concentration of H2O times mass average velocity of H2O plus the mass concentration of D2O multiplied by negative 1.0008 meters per second, all over the total mass concentration, which is 1,055 kilograms per meters cubed. And that value is negative 5.217 times 10 to the negative 6 meters per second. And since we now know the mass average velocity of the system and the total density of the system, we can solve for the total mass flux, which is the total mass concentration, which is 1,055 kilograms per meters cubed, multiplied by the total mass average velocity, leaves us with a mass flux of negative 5.5 times 10 to the negative third kilograms per meters squared per second. In the next part of the problem, we are being asked to make an order of magnitude estimate for the maximum driving force for fusion. So to start out, we know the equation for driving force, and that is the sum of mass of I times molar diffusive flux of J minus the mass of J times the molar diffusive flux of I all over the concentration multiplied by the Stefan Maxwell diffusivity of I and J. So writing out the summation for our two components, we have x of 1 mass or molar diffusive flux of 1 minus x of 1 mass diffusive flux of 1 over the molar concentration times the Stefan Maxwell diffusivity of 1 and 1 plus x of 1 molar diffusive flux of 2 minus x of 2 molar diffusive flux of 1 over concentration times the Stefan Maxwell diffusivity of 1 and 2. So looking at this, we can see that these two values are equal, making that 0. And since this is a binary mixture, x of 1 plus mass of 2 is equal to 1, or mass of 1 is equal to 1 minus x of 2. The same holds true here where the sum of the molar diffusive fluxes is equal to 0, making J2 equal to negative J1. So plugging in that information, we get the driving force is equal to negative molar diffusive flux of 1 multiplied by 1 minus x2 minus molar diffusive flux of 1 times mass of 2 over concentration times the Stefan-Maxwell diffusivity. And also, this is a ideal system, making the Stefan-Maxwell diffusivity of 1 and 2 being equal to the diffusion coefficient of 1 and 2. So plugging that information into here and making it simpler, get negative J1 plus J1 x2 minus J1 x2 over concentration multiplied by the diffusion coefficient of 1 and 2. So these two values cancel each other out, which leaves us with the equation of negative molar diffusive flux of 1 over the molar concentration multiplied by the diffusion coefficient of 1 and 2. And since we were given a molar diffusive flux of, per se, H2O, we know that that is 2.78 mole per meter squared per second over the concentration of water, which is 55,555 moles per liter, multiplied by the diffusion coefficient for liquid, which is 10 to the negative 9 meters per second. And this gives us a driving force magnitude of negative 5.004 times 10 to the 4th. In the third part of the problem, we are being asked to graph different mass transport profiles in relation to H2O and D2O at some position X within the capillary tube at different times. So in this column, we'll have the initial time. Here we'll have intermediate, and here we'll have final as time goes to infinity. So starting out with the mass concentration, we know the mass concentration of water is 1,000 kilograms per meters cubed. We know initially the mass concentration of water stays constant until it reaches the halfway mark where it starts to meet the D2O. Since it hasn't been given the chance to fully mix yet, since this is the initial graph, it goes all the way down to 0 and continues onward past that point. Now when it comes to D2O, we know that mass concentration to be 1,110 kilograms per meters cubed. And it's basically the same as for H2O's mass concentration, but opposite, where it starts at 0, between 0 to 5, because that is where the liquid H2O is, and then goes all the way up at 5 until it reaches 1,110 kilograms per meters cubed, and then across, because it hasn't been given a chance to mix yet, since this is the initial condition graph. At an intermediate, starting at the same locations of 1,000 and 1,110, we start with water. And since that has been given, since now the reaction has been given a little bit more time to occur, it is a less steep slope as the two reactants have been given time to mix with each other. And D2O is just the opposite, with them interacting, being equal at the 5 centimeter mark. And with this going up to the initial density of D2O, which is 1,110 kilograms per meters cubed. And so looking at the final graph, we know the final densities of H2O and D2O, so after solving it for them in the first part of the problem, and that is water is 500 kilograms per meters cubed, and D2O is 550 kilograms per meters cubed. So at time is equal to infinity, both of these substances have been given time to mix with one another completely, making it a constant mass concentration of each substance along the entire plane of the capillary. Next, we'll be looking at the molar concentration of H2O and D2O. And these two graphs are very similar to the mass concentration, except the mass or the molar concentration of H2O and D2O are equal. So these two graphs are going to look almost the same, except the starting points are equal now for H2O and D2O, since their molar concentrations are equal to one another. All right, and the same effect in the intermediate graph, where both H2O and D2O start and end at the same position. And lastly, the final condition graph. And stating it one more time, the molar concentrations of the two are equal, making these two lines right on top of one another. Now we'll be discussing the mass transfer profile of the molar diffusive flux when it comes to the intermediate, initial, and final versions of the graph. So we know that both substances start out at 0 centimeters. And we know the maximum molar diffusive flux, and that is 2.78. And then adding the opposite in there as well, negative 2.78. Initially, water does not have any molar diffusive flux until it reaches about the 4 centimeter mark, where it goes up to 2.78, then back down to 2.78, then back to 0, because the water hasn't been given the chance to disperse that far into the tube yet. And the same is true for D2O, except negative. And this is because the total molar diffusive flux at all times is always equal to 0. And the intermediate graph looks pretty similar, except there is a greater area of molar diffusive flux, with the same boundaries on the graph being 0, 2.78, and negative 2.78. In the intermediate, the two liquids have been given the chance to interact a little more, making the molar diffusive flux start at a lesser position on the graph, causing the same slope as before, not the same slope, but causing the same point as before at 2.78 molar diffusive flux. And the same is true for D2O in the opposite direction. And again, this is just because these two liquids have been given more of a chance to intermingle with each other and react throughout the entirety of the tube. Now, the final condition, where t is equal to infinity, assuming that all of these liquids are now intermingled equally within this tube, there is no more molar diffusive flux, making them both equal to 0. Now, when it comes to the total mass flux of the system, we know that the initial value is 0, and we also calculated the maximum mass flux, which is negative 5.5 10 to the negative third. And so this graph, initially at point 0, starts out at 0, and then as it reaches the halfway mark where these two liquids are starting to mix, it dips down to the negative 5.5 10 to the third, which is the total mass flux, and then goes back up to 0, and then continues on. And the reason for the steepness in this slope is because this is the initial condition, and at this point, 5 centimeters, both the two liquids are starting to mix at the most rate. For the intermediate condition, it's about the same, except with a less steep slope than before, ending at the same point of negative 5.5 10 to the third. And this isn't as steep of a slope because at the time equals 60, the two liquids haven't given enough time to interact with one another to make the mass flux start earlier in the capillary. And then the final, which starts at 0, both of the liquids have intermingled completely, and there is currently no more mass flux in the system.